Welcome friends. So we are discussing the AC signal or AC excitation on different networks R, L, C, RL, RC. So now we shall start the RC network with AC excitation. What will be the nature or what will be the relationship between voltage and current, and finally what is the power consumed in series RC circuit. So let us say we have a series RC circuit, just like we have a series RL circuit. Now we have a series RC circuit. Voltage appearing across R is VR and voltage appearing across C is VC. No, so similarly we can write V is equal to the supply voltage is equal to VR plus VC. So from the knowledge of the previous phasor relation, you see this is for resistance, for resistive network. For resistive network, voltage and current are in same phase. For inductive network, voltage current should be lagging by 90 degree than voltage, and then capacitive network we have current should be leading by an voltage by an angle of 90 degree. Now in this case we have now series R and C, right? This is supply voltage. Now if this is the current flowing, and this is the VR, this is the VR. So VR and I should be in this direction. I is this and VR is this. Simple, because they are in its phase. Now if this is VC, then current flowing through a capacitor should be 90 degree leading. So therefore VC should be directed along this direction. So phasor summation of VR and VC, V is equal to VR plus VC, we have in this direction. We are getting something reverse as compared to the previous one, and this angle is phi, which is called power factor angle. Okay, so VR is equal to I into R, VC is equal to I into, now it is, you see this VC, now VC is rotated by an angle of 90 degree in negative direction. That is why a term is called minus J XC, minus J XC. Minus J XC. So if you take common I, then it should be R minus J XC, which is equal to I into Z. So in case of a series RC circuit, we have Z is equal to, impedance is equal to R minus J XC. So here it is R, we have J XC in this direction, J XC in this direction with a minus sign, of course, because it is giving you this direction. clockwise direction, and this is your Z, and this angle is phi. So the magnitude of Z is given by r square plus minus xc whole square, and the angle is nothing but tan inverse minus xc by r. This is the series impedance for the series RC circuit, R minus jXC. So we have with excitation, so this is one mistake. It should be XC, but it should be not omega L, it is 1 by omega C. XC we have already previously defined or proved that XC is equal to 1 by omega C. From here, capacitance will provide a reactance of 1 by omega C. So this is one mistake, it should be corrected. R minus J by XC. So it is the magnitude and it is the angle. Now from the phasor diagram, if you consider what we have observed, it is actually the current phasor and it is actually the voltage phasor. This angle is phi. So voltage phasor is taken as reference omega t. So now in case of a series RC circuit, current is now found to be leading. So due to this reason, it is written Im sin omega t plus phi, because it is a leading. So if you solve the instantaneous power equation, we shall get a similar relation. So 2 sin C sin D. Now we are getting the same expression. Now as far as this cos 2 omega t concerned, it will be 0 after integrating, and this will be only coming out as outside, so it will be V into I cos phi. The same relation, V I cos phi, where V and I stands for the RMS value. So now the salient points of the of the series RC circuit: current flowing through the series RC circuit is leading by an angle phi. In case of a series RL circuit, it was lagging, but in case of a series RC circuit, it is leading by an angle of phi. The range of phi is same. It can take any value between 0 to 90 degree depending on the value of R and L. If R is more, phi is most likely to be tilted towards 0 degree. If C is more, phi is most likely to be tilted towards 90 degree. That is the difference. So which means the phase displacement between voltage and current is phi. Now in this case it is leading because current is leading now. Current is leading now than voltage. Phi is called power factor angle. Now power consumed for series RC circuit is same. In that case of series RL circuit, both are VI cos phi. Power factor definition remains same. It is the angle between voltage and current phasor. Now it is power factor. Now in this case it is leading. Power factor in this case it is leading. It can take this value in between 0 to 1 depending on the value of R and C. So this is series RC circuit. Now with our last topic, that is series RLC circuit. Now we have all the elements are present. R, L, C, all are present here. what will happen? So if all are present, then we have a R, this is R, we have L, this is L, we have C, this is C, then we have a supply voltage P, a current is flowing I. Now voltage drop across resistance is VR. Voltage drop across inductance is VL. Voltage drop across capacitance is VC. So supply voltage V, it is given by the phasor summation of VR plus VL plus VC. So we can draw the phasor summation. So you take I as a reference phasor. Now as far as this VR is concerned, it is in this direction, that means in phase with I. VL should be lagging. VL should be lagging. Sorry, VL should be leading than current, because inductive current should be lagging. So inductive voltage should be leading in opposite way, we can say, and capacitive voltage should be in this direction. Now we can find that VL and VC are directly in opposition to each other. VL and VC is directly in opposition to each other. So we take a term is called VL minus VC. So let us say this up to this, it is up to this, we evaluate VL minus VC. Up to this we evaluate VL minus VC. So this much is nothing but VL minus VC. So phasor summation of VR and VL minus VC will be the supply voltage. So the V should be is equal to VR square plus VL minus VC whole square whole under root. This angle is phi, which is power factor angle. So this is the phasor diagram of series RL circuit. Because VL and VC are directly in opposition to each other, so we can take the difference between them, VL minus VC. So if this is VL minus VC up to this, then this VL minus VC plus VR, if you add them by phasor means, it will give you the supply voltage V. And formula is V is equal to this VR square plus VL minus VC whole square under root. Now one question comes, why VL minus VC is written, why not VC minus VL? Why not VC minus VL? Is in practical cases, inductance is dominant over capacitance. Dominant over capacitance. It is by virtue of nature. So that is the reason, if you take any load, let us say motor, let us say refrigerator, let us say AC, whatever load, they are highly inductive in nature. It is the by virtue of the nature. So that is why in practical cases in our electrical system, inductance is dominant over C. So that is why it is expected that voltage drop appearing across inductance is greater than voltage drop across capacitance. So that is why it is recommended to take VL minus VC. And this angle is phi. So again we can see that phi is lagging. This current is lagging by some angle phi. So that angle is called power factor angle. So we can write now, we can quickly discuss. So this is the equation, fundamental equation. PR is equal to I into R. EL is equal to I into XL. VC is equal to I into XC. Then if you take common, R is equal to I into R plus J XL minus XC. XL minus XC is called net reactance. Net reactance. So this X is called net reactance. X is called XL minus XC. It's called net reactance. So in case of, yes, it is called net reactance. So Z is equal to R plus JX. R plus JX for a series RLC circuit. And similarly, so what is Z? Z is given by this formula. Z is equal to root under R square plus X square. So R square plus, now what is X? X is equal to XL minus XC whole square. Now what is XL? XL is equal to omega L. Omega L. What is XC? XC is equal to 1 by omega C. So that is the reason this relation, R square plus omega L minus omega C whole square. And phase angle becomes tan inverse X by R. So phase angle, it is tan inverse XL minus XC by R. So from the phasor diagram, it is observed that current is lagging by some angle of phi than voltage. So we write this equation. So similarly, it is guaranteed that power consumed in a series RLC circuit is also V into I into cos phi. Just like we have found in case of series RL and RC circuit. Now, what points to be remembered? Key features: current flowing through the series RLC circuit. Now in this case it is may lead or lag depending on the value of L and C. Okay, it is never guaranteed that it will lag. It is never guaranteed that it will lead. It may lead, may lag depending on the value of L and C. If L is dominant, then it will be lagging. If if L is lagging, or if reactance is dominant, power factor will be lagging. And if capacitance is dominant, power factor will be leading. But most of the cases this happens because of natural loads. Okay, they are in the inductive nature. Now power consumed in RLC circuit is same as that we have found in case of RLRC, which has already been spoken. and power factor may be leading or lagging depending. Just we have mentioned that since this current flowing through may lead or lag, because of that power factor may also lead or lag. Power factor may also lead or lag. You see, if the capacitance is dominating, then VL minus VC will become VC minus VL, VC minus VL. Then this phasor will be directed along this direction. So this supply voltage will be directed along this if reverse things happen. So for that case, current becomes leading. So its power factor also totally depends on the value of RLC. Now quick recap. If we have R, we have phi is 0, that means phase displacement between voltage and current is 0. Now we have only resistance is equal to R. Power as you consumption is V into I, that is the RMS voltage of voltage and RMS of current, and power factor is always 1 because cos phi is 0, so power factor becomes cos phi, so cos 0 is 1, that is why it is 1. Now if we have only inductance present, so phi is 90 degree lagging. Why? Because current is lagging. This is current, this is voltage. Now in case of a inductance, there is no resistance, there is no impedance, we have a reactance to offer, so which is XL, which is omega L into 90 degree. Omega L, and the rotation is 90 degree, which is represented by J. So J omega L is as same as written. It is omega L, its magnitude, omega L magnitude, and J is contributed by an angle of 90 degree, positive angle 90 degree. That is why it is written here, omega L at an angle 90 degree. Power consumption in case of an inductor 0. Power factor is also 0, but in case of inductor, power factor is lagging. Now when we have a capacitor, power factor angle is 90 degree, but it is leading now. Why? Because this is the phasor diagram we have observed. Now in case of a capacitance offers a reactance of Xc, which is equal to 1 by omega C. Xc will offer a reactance of 1 by omega C, which provides a rotation of minus 90 degree. Power consumed 0, power factor will be 0, but it is leading. Now if we have a series RL, then power factor angle, power factor angle phi can take any value between 0 to 90 degree depending on the value of R and L. If R is more, phi most likely to be tilted towards 0 degree. If L is more, phi is most likely to be tilted towards 90 degree. And since the current is lagging, then the angle should be lagging in nature. Now in case of a R and L, it will provide a impedance. Which is equal to R square plus XL whole square. The angle is given by tan inverse XL by R. Now power consumption is in this case now V into I cos phi. And power factor becomes cos phi, which is lagging in nature. Now in case of RC circuit, now power factor angle or the angle between voltage and current can take any value from 0 to 90 degree. Now in this time current leading than the voltage. If R is more, it will be most likely to be tilted towards 0 degree. If C is more, phi is most likely to be tilted towards 90 degree. Now this is the reactance of or impedance of series RC circuit which is R square plus XC whole square, an angle of minus XC by R, tan inverse minus XC by R. Power consumption is also V into I cos phi. Power factor, in this case it is leading. Now finally we have RLC series circuit. Now the phi, its take can any value from 0 to 90 degree depending on the value of L, C, R. It could be leading, it could be lagging, it could be anything depending on the value of R, L and C. It will provide an impedance of this value, also provide an angle. Also in case of a power, it will be dissipating a power of V into I cos phi, and power factor remains cos phi. Depending on the value of L and C, it will be lagging or leading. If it is inductive in nature, it is lagging. If it is capacitive in nature, it should be leading. So with this, I am ending here. So in the next class, we shall see some problems on this. Thank you.